This is the second of my waiting line or queuing theory videos, and it'll introduce some of the mathematics or some of the models that we use to calculate some of the factors that we're trying to understand when we are assessing queuing, when we're assessing service landscapes. And so the first one sort of went over some of the concepts that we need to think about. This one's going to introduce the math, and then there'll be a couple of more afterwards that are specific examples of questions that I'll work through. So without further ado, let's begin right away on some of those mathematics. So the first thing we need to think about is the probability of arrival. So how many people are going to show up in our system, which obviously has an effect on the lines. So customer arrivals are usually random and can be described by what is called a Poisson distribution. And the Poisson distribution looks like this, which says the probability of n arrivals, so that's the number of arrivals, in time t. So what you're looking for is the probability of a certain number of arrivals in a given amount of time. So this is time t. Lambda is the average number of customer arrivals per period, or the mean. E is a constant that you'll see on your calculators, to the negative lambda t. So lambda to the times t to the n over n factorial. That'll be a key you have on your calculator as well. And factorial, 5 factorial is simply 5 times 4 times 3 times 2 times 1. And so this looks complex, but gives you the probability of a certain number of arrivals in a certain amount of time. That can be used to look at waiting times. It can also be used to say if we are a high service level company and we know within an hour we're going to usually get, we want to know what the probability is, we're going to get 4 arrivals because we have 4 people on staff, those sorts of questions. E is a constant in your calculator, but it is also equal to 2.7183. So let's take a look at how we execute that. So we have an arrival rate, which is 2 customers per hour. And this is probably one of the biggest tricks in queuing theory. You want a rate, and a rate is something per hour. If I was to say you have an average of 1 customer arrive every 30 minutes, you would have to convert that to a rate by taking the inverse, which is 2 customers per hour, and that is lambda, and we're going to use lambda in almost every model. So the probability that 4 customers arrive, that's n. Time period is t is 1. We can do that for any time period, but in this case we're just using 1 hour. So the probability that n customers arrive in an hour is lambda, which is 2, times 1 to the n, which is 4, over 4 factorial, times e to the negative 2, 1. When you're calculating this, when you're punching it into your calculator, I will almost always do e to the negative 2, 1. You need to put this in brackets when you're punching it into your calculator so that it works well and you get an accurate number. I will almost always calculate this first and then calculate this second. You have to make sure you get the orders of operation right if you're putting all of them in. So I think you're usually better off calculating it in steps to get the order right. So as you can see, the probability of 1 customer arriving in an hour is 0.271. That's pretty high. The probability of 2 customers arriving in an hour is also 0.271 because on average we have 2 customers coming per hour. So we might have more, we might have less. this is the probability that exactly 2 will arrive is 0.271. So the probability that 1 or 2 will arrive will be the sum of those two. And the probability that 4 customers arrive in an hour is pretty low, 0.09, because on average 2 arrive, there will be almost 10% of the time 4 customers that arrive. So that probability, while that formula looks a little bit scary, the probability is relatively straightforward to interpret. The next thing that we're interested in is the distribution of service time, operations time. So that's the amount of time that you spend with a customer. And that is usually described by what's called an exponential distribution, which is shown right here. And so it's the time required to complete the service. So not all customers take the exact same amount of time. So we have a distribution. Some customers take longer, some customers take shorter. That can be called service time or processing time. So within the exponential distribution, we have the probability that service time, small t, actual service time, is less than or equal to big T, which is the target service time, is equal to 1 minus e to the negative mu t, where mu is the mean number of customers completing service per period. So that is the service rate. So lambda was the arrival rate, mu is the service rate. And again, you have to think about it in customers per hour. So if I tell you that the average service time for a customer is 30 minutes, it doesn't have the word per in it, it's not a rate, and we would take the inverse of that and say our service rate is an average of 2 customers per hour. And I'll show you examples both in this slideshow and in ones where I do some specific examples. T is the service time that we're interested in and is the actual service time, and big T is the target service time. So let's look at an example here. We have an arrival rate of 2 per hour. We have a service time or service rate of 3 per hour. So the probability that a customer requires less than 10 minutes. So the probability of T, actual service time, is less than or equal to T, which is 10 minutes, is equal to 1 minus e to the negative mu t. Now, this is 10 minutes, and these rates are both in hours. And so we need to be sure that we have the same units. The first thing I said you need to be really careful of is that you have rates. The second thing you need to be really careful of in queuing theory is that your units are the same. So in this case we have 10 minutes, so we don't put 10 in here because these are hours. And so we convert 10 minutes into hours and we get 0.167. That's the only other trick that I can throw into a queuing theory question. So the probability that a customer service time is less than 10 minutes is equal to 1 minus e to the negative 3 service rate times 0.167, the target time, is equal to 0.39. Now, what this tells you is that the probability that we will take less than or equal to 10 minutes is 0.39. That doesn't tell us the probability of it taking exactly 10 minutes. It is the probability that it is 10 minutes or less. And so if 10 minutes is our target, we know that only 40% of the time we're going to achieve our target. And so I'll show you some examples in my next video where I work through some examples, but there are several different things we can do here with respect to calculating service time probability. So our expected service time is 20 minutes because we have an average of 3 per hour. And the probability that it takes less than 10 minutes is 0.39. So 40% of the time we finish a customer in less than 10 minutes. So we can establish standards. We can look at changing the service rate by improving training or adding another support person or all sorts of things. And then we can evaluate whether we're achieving the targets that we want to achieve. So now we're going to talk about actually calculating how many people we have in line and how long that they wait on average. So in that we have line length, so how many people are waiting in line, number of customers in the system, and so that is line length plus the number of customers being served, time they spend waiting in line, time they spend in the system, and the time they spend in the system is expected time in the line and expected time in service. And the last thing is service facility utilization. And utilization is how busy we are, and the busier we are, the lower our service levels are because people end up having to wait in line. So the higher utilization is, and utilization is good because it lowers costs, the lower service level is. And so we will make strategic decisions depending on what we prioritize as service levels as a company in order to deliver the kind of service that we want to as a company. So long lines aren't bad, and high utilization is good in some circumstances, but it might not be good in circumstances where we have a high value customer and we don't want them ever to wait. So there are no absolutes here. There are a variety of things that we need to think about. So let's look at the singles workstation model. It is the simplest one. It is the one that I spend the time on in introductory operations class, and it explains the concepts. The formulas get much more complex, and I'll show you at the end of this presentation. The formula gets more complex when we do multiple servers and all of those sorts of things. They're all possible, but we're not going to cover them here. So this is the service process termed a single server model, and it's what we're going to focus on. And the assumptions of this is the customer population is infinite and all customers are patient. What that means is there's no limit on people who might come in, and nobody will walk away if they have to wait too long. Both of those assumptions make this easier to work with. If customers are impatient, then we have to add the calculation for the probability that they're going to leave if the line gets too long. And if the population isn't infinite, it affects arrival rates and the number of people who will arrive. Customers arrive according to a Poisson distribution, which we looked at already, with a mean arrival rate of lambda. Operations or service time distribution is exponential, which we already looked at, with a mean processing rate or service rate of mu. Customers are served on a first come, first served basis. That's the priority rule. And the length of the waiting line is unlimited. So there's, if we, depending on the circumstances, there's no constraint on the line. There's no physical constraint on how many people can wait in line. And this is tied a little bit to customer patience. So then we have let's look at some of the formulas that matter. Again, we need to make sure we have rates. Average capacity utilization, rho, is equal to lambda over mu, which is arrival rate over service rate. If your arrival rate is bigger than your service rate, you have an intractable problem. You have people arriving more quickly than you can serve them. It gets back to the example I used before. If you've ever Googled the I Love Lucy chocolate thing, you have chocolates arriving faster than you can put them in the box, and the line just becomes infinite, right? If you have 10 people arriving per hour and you can serve 5 people per hour, then the line is just going to get longer and longer. You will never catch up. So this should always be less than this, and so rho should always be between 0 and 1. If you get a number that's not between 0 and 1, you have an intractable problem, or you have calculated your rates incorrectly. So then again, look at units and make sure that you have a rate and not the inverse of the rate. And I'll show you that in the examples. So utilization is how busy the system is. The closer that is to 1, the closer the arrival rate is to the service rate, and the longer your line will tend to get. So the probability that there are n customers in the system is 1 minus rho times rho to the n. And we'll show you a couple of examples in a second. The average number of customers in the system, L, is equal to lambda over mu minus lambda. So as lambda gets bigger, the number of people in the system gets bigger. Average number of people waiting in the line is LQ, which is simply rho times L. So if you want to know just how long they wait in, the last one was time in the system, which included time in the line. This includes just the time they're spent waiting in line. The average time spent in the system, including waiting time and operations time, W is equal to 1 over mu minus lambda. And then similarly, the average time waiting in line is simply rho times W, or the utilization times the average time in the system. So let's look at some examples here. We have a single channel, single phase system calculating operating characteristics. We're trying to understand the lines and that sort of thing here in the model. So we have an arrival rate, 30 people per hour. We have a service rate, 35 people per hour. Those are both rates. We have an arrival rate that is less than the service rate, so we are happy with what we have here. Our utilization is 30 divided by 35 is 0.857, or 85.7%. That means 85.7% of the time we have a customer in the system. So the probability that there are 0 customers waiting is 1 minus rho times rho to the 0. Rho to the 0 is 1. So you have 1 minus rho. So this is the probability that there is at least 1 person in the system. And the probability of none is, you can't see it here on the slide, but it will be 1 minus 0.857. So the utilization is 1 minus the probability that there is nobody in the system. So utilization says, what's the probability that we are going to have someone in the system and that we're going to be busy? The higher it is, the less idle time we have. The higher it is, though, the more likely we are to have a line. And so those are the trade-offs that we need to think about. There was the... Oh, sorry. The average number of people in the system, L, is arrival rate minus service rate, divided by service rate minus arrival rate. So we have 30 over 5, which is equal to 6. So on average, we will have 6 people in the system. Average number of people in line is just the utilization times the average number of people in the system is equal to 5.14 customers. We don't round that off. I know we can't have 0.14 of a customer in a line, but because these are averages and we want to accurately reflect the average, this isn't the actual, this will vary because we have a probabilistic system here. The average number of people in line is 5.14. We want that number to say, okay, how much space do we need to have for people to line up? And so we think about those sorts of things. Average time in the system is 1 over mu minus lambda is equal to 1 divided by 35 minus 30 is equal to 0.2 hours. And then the average time in the line is just rho times the average amount of time in the system. is equal to 0.171 hours. So on average, people wait 0.171 hours. On average, it takes them 0.2 hours, 18 minutes, I think that is, if I'm thinking about it correctly. No, 12 minutes, sorry, 12 minutes. That means on average, from when they arrive to when they leave is about 12 minutes, and we can say, does that make sense? Are we happy with that service, if that service experience? So we can do some other things here. As an example, if we have an arrival rate, lambda is equal to 30 per hour, we have an average time in the system is equal to 8 minutes. We can then calculate and solve for what our service rate is. So this is just a way of, and I'll show you that in the examples, it's a way of making sure you understand the process. It is also a question you could ask. You know, you could say, our expected arrival rate is 30 customers per hour. We want our service standard to be 8 minutes. We want our average time in the system to be 8 minutes. What service rate do we need to achieve in order to meet our desire to meet that 8-minute service time? So it's not just an abstract question to make sure you understand the equation, but it can be a real world problem as well. We have this arrival rate, we want to set this standard, what should our average service rate be, and then we can determine what we need to do to achieve that. The probability of more than 4 customers is equal to 1 minus the sum of the probability that there is 0 customers, 1 customer, 2 customers, 3 customers, 4 customers. So if we know that because here we have discrete probabilities, right? In this case, we can't have half a customer in the system. We either have 0 customers, we have 1 customer, we have 2 customers, and so on and so on. So if we want to figure out the probability that we have more than 4 customers, we first have to figure out the probability that we have 4 customers or less, and we do that by calculating the probability of 0 customers, 1 customer, 2 customers, 3 customers, 4 customers, subtracting that from 1 because there has to be either 0 or some number of customers, and we know all those probabilities sum to 1. So in this circumstance, we have rho is equal to 30 divided by 37.52, so our utilization is 0.8. And we then have that calculation where we have each of these, right, we have that formula. I'll work through an example for you in a second. So the probability of 0 units in the system, that is that the service unit is idle, is 1 minus lambda over mu, which is 1 minus the utilization rate. I talked about that already. The probability that n is greater than k, the probability of more than k customers in the system, where n is the number of units in the system, you can either do it by that formula I showed you before, the sum of all of those individual ones, or you can do the utilization, this is the utilization, to the k plus 1. And I'll show you examples. That one's much easier to explain in an example. So if we have a multiple, those are the things that I would expect in my course that people would understand and be able to determine. In fact, the multi-channel single-phase system has has similar concepts. It's just the formulas become a little bit more tough. So let's talk about it just for a second. The single system has only one phase. There are S identical servers, which means that we have, if you're thinking about a grocery store, you have several cashiers. Mean service time is equal to 1 divided by mu, right? Mu is the service rate. Service time is 1 over that service rate. And the service rate is S times mu, right? We have that many people. We can serve, each person can serve 3 customers per hour. If we have 4 of them, the whole system can do 12 customers per hour. And you need to make sure that this, just like when we just had 1 S mu exceeds the arrival rate, or we have an intractable problem. The reason so the utilization here is approximately the same. It is the arrival rate over S times the individual service rate. So our system service rate is the number of servers, and then the probability of 0 customers is much uglier than it was in the single server case. So it's not hard to calculate. It allows you to do it in different circumstances, but in my course, I generally want you to understand the single server model so that you understand the concepts that underlie these queuing theory models and can articulate what it means if waiting lines get longer or shorter, or time in the system gets longer or shorter. So 3 things to think about. Do we have a rate, or do we have a time? And then we need to make sure we have rates. Do we have similar units, or is one thing in minutes and the other thing is in hours? That's the only trick, the only 2 tricks I can put in. And then just systematically work through those parameters, and you should do. Queuing theory is not hard. It just means you need to understand each one of these concepts. That's it. Quick introduction to these math problems, and I will go through a couple of examples in separate videos of the types of questions that you can get in these cases to help you work through what you might see on an assignment or an exam. That's it.